All right, so we are here at this lesson where we are still going to be doing that kind of problem where we apply our understanding in calculus in taking the definite integral into calculating the volume of a solid that is generated by rotating a region, okay, around a given axis. However, this time we are going to approach the problem. We're going to come up with a solution that is completely different from those solutions we have learned previously. Okay, and so allow me to introduce the problem right here. Let me make a quick brief sketch here, and I will be a little more clear in terms of what it means by the completely different from the other solutions. Okay, but so the method that we're about to learn here is called the cylindrical shell method. So we are going to be using cylindrical shells. Okay, we're using cylindrical shells, and then this is a method to calculate volume. So many textbooks, many standard calculus textbooks refer to this as the cylindrical shells method. Okay, so but as I was saying earlier, the idea now is just like some of the application we have seen before. The idea here is that we have a region, okay, and let me draw a region that is a little easier to draw because I will have to make quite a few different versions of that same sketch here. So how about we have a region like this, okay? All right, we have a region, and then there's our region, the area of the region here, and then we're gonna take the region and rotate around an axis, okay? And so I keep talking about just earlier before this point, in this video lesson, I kept talking about and I introduced this problem as we are still doing this problem. That means we have learned other methods prior to this video lesson to handle the volume of the kind of region of the solid where, so let's say we take this area and we're rotating that around the x-axis. So some problems we are required to take the region here and rotating it around the x-axis where we create, okay, so I'm not the best drawing artist out there, but so we can rotate the region like that to create a solid as described in the picture here. Okay, so that's the case where the problem requires us to rotate the given area here around the x-axis. But the same region here we already learned previously by, how about let me navigate to the other board, and I'm going to try to reconstruct the closing up picture of that region. Okay, and so that same region there, we also learned the method to take the area enclosed in this region and rotate that around the y-axis. So some problems requires us to rotate the region here around the y-axis. So in that case, we are going to produce a picture like this. Okay, and so the methods we've learned earlier, the methods we've learned prior to this point, and so needless to say, this lesson here would be better understood, even though it is completely an independent method itself. But I would like to make the connection between the method we're about to learn here with the earlier methods that we have learned. Okay, and so of course in the way how it is, then some method has to be learned before some other methods. But in my own teaching style, usually I deliver this method here after I teach the other methods, and it's all about how to find the volume of a solid that's generated by rotating a region around a given axis right here. So the previous methods we have learned, as I've been mentioning here in this lesson, is that it's the washer or the disc methods. Okay, and so before we can really understand what the cylindrical shell method is all about, then let's look back at the method that I have introduced for everyone learning with me before. So, and again, just in what I'm saying, in my teaching style, then usually this method is taught, and then it's for students of my class. Usually this method is learned after you have seen the disc or the washer method. And so let's say in this case here, if we are rotating this region, this known region, enclosed region, and of course region is enclosed between curves or graphs, okay, and so if we take this region and rotating around the x-axis, then the fundamental ideas of disk or washer methods, if we're using disk or washer method, then we're going to create a stripe. We're going to create a stripe to draw through the region. So here's our stripe. Okay, we create a stripe that's drawn through the region, but we have to make the stripe perpendicular. We have to make the stripe perpendicular with the rotation axis. Okay, so a couple of common terms a couple of common terms are still existing here. As long as we're still taking a region and rotate around a given axis, then our rotation axis here, yes, it's that same term I have to use again. So the x-axis here in this case is called the rotation. Okay, the rotation axis. Okay, it could be the x-axis, it could be the y-axis. And outside of class, you know, once you have mastered the skill, you are also given the kind of problem where the rotation axis is not necessarily the x or the y-axis. Okay, but now here we have the rotation axis. So the fundamental idea of either disk or washer method is that we through at any point, you know, inside the region here, we're gonna draw a stripe. Okay, we're gonna draw a stripe through the region and to reach all the way to the rotation axis. And one more requirement: it has to be perpendicular to the rotation axis. That's the main requirement of the disk or the washer methods. And I don't mean to summarize the disk or the washer methods here, but then we need to look back at that method so that we can understand how this method we're about to learn here will be different. Okay, and so in that way, what I'm seeing here, it would be a washer if, so in my explanation before, the same stripe going through the region, if we recognize, it's just the way how the drawing is, if we recognize any part of the stripe that goes outside of the region, then consequently when the rotation happens, we will create a washer. Okay, so just like that. So that's why, you know, if you want to understand clearly what the washer or the disk method is all about, view that lesson of mine, those two lessons of mine when I was going over the disk or the washer method. So, but generally, anytime that but this washer method is all about we creating the stripes or any stripe through the region and reach to the rotation axis and be perpendicular with the rotation axis. And then, just like that, if any stripe has to go through, if any stripe has a part that's outside, so that's why I'm doing dotted here. If any stripe has a part outside of the region, okay, then rotating that, we will have an empty space, and our cross section here becomes instead of a disk, our cross section become a washer. Okay, and in other case, there are regions out there. There are regions that we learn where it could be something like this. So at some part of anywhere that the stripe stays completely inside of the stripe that's perpendicular to the rotation axis, stays completely inside the region, then rotating that stripe, we will have a disk. And that's why in my teaching style, usually I explain disk and washer method is really the same method. It's just the difference about whether the stripe has some part being outside of the region or the stripe is completely contained inside the region. Okay, so that's the general idea about the washer method. And so in the other picture that I put on the other board, it's the same. So if in case that our rotation axis is the y-axis, okay, so rotation axis is here. So we're rotating around the y-axis, and this axis here is called, again, in that old term, rotation axis. Okay, then what we do here, we draw the stripe. So anywhere at any instant, anywhere in this region here, we're going to draw a stripe, and the requirement for that stripe is to make the stripe go through the region and reach all the way to the rotation axis and be perpendicular, form a 90-degree angle. Okay, and so just like that, if the stripe has a part, or if some part of the stripe that we're currently looking at, if some part of the stripe is outside of a region like that, okay, then we have this stripe here. Consequently, when we're rotating, we will end up with a washer. Okay, otherwise Otherwise, if we're looking at a region where it's looking like this, where any stripe, or at any stripe, if we have the stripe completely contained in a region, okay, then that stripe, once we're creating this, when we're rotating it, it becomes a disk, okay. And so that's why, once again, disk method and washer method to me is really the same method. It's just the matter is whether your stripe is going to give you a disk, or your stripe perpendicular to the rotation axis will give you a washer when you're rotating it, okay. But now the method we're about to learn here. So again, I'm going to have to erase all the stripes here, because the stripes we're using here, the critical thing is they have to be perpendicular with the rotation axis, and that's the part. And then some stripe create for us the disk, some stripe create for us the washer as we rotate it. But let's say now we are looking at the same rotation. But now when we depart from disk or washer methods right here, and let's look into cylindrical shell method, then the primary idea that makes this method here different from disk or washer method is that, so here's our area again, okay. We are still going to draw the stripe. So, but this time we are going to, through the region, again, we're going to draw the stripe, okay. And of course, this time the stripe will, okay, so allow me to put down the stripe first. All right, so observe my drawing closely. What have I done here? I drew my stripe here, and we can have many stripes like that, infinitely many stripes through the region, and these stripes are all parallel. Okay, these stripes, the same with the disk or the washer methods, all the stripes supposed to be parallel because they're all perpendicular to the rotation axis. So here we are still doing parallel stripes, okay? But this time the parallel stripes are, any of the stripes here is parallel to the rotation axis. Unlike the case of this washer method. So this washer method, the stripes go like this if the rotation axis is here. Okay, then the stripe goes like this. That's this method, disk or washer method. But now when we're rotating, when we're about to use the cylindrical shells method, I'm about to get really into the details here. The primary thing that makes a difference with the other methods, okay, with the disk and the washer method, is that the stripe, any stripe that we place in the region has to be parallel, okay? Any stripe. So, or all stripe. So any stripe is the critical requirement here. Any stripe is parallel. All right, it's parallel with the rotation axis. All right, any stripe is parallel with the rotation axis, or another way of saying is all stripes that we're drawing are parallel to or parallel with the rotation axis. Okay, and that's why, of course, it makes sense that way with elementary geometry, that all of these stripes in the end consequently turns out all parallel. Okay, and so in that way, now let me put away this note right here, and this note is important, but sadly I have to erase that. So go ahead and rewind the video if you need to take down that note, if you need to note down that note right here. But what will be the picture consequently? And at this point, it is the unavoidable that you gotta somehow or in some way push beyond your imagination, right? I mean, push your imagination a little bit beyond what you normally do. Okay, that's what I mean right there. And so let's imagine what's going to happen. What kind of picture is it going to be created if we take this only one stripe? If we take this only one stripe and rotate, the whole stripe, now known to be parallel to the rotation axis, the entire stripe is now currently known as a requirement to be parallel to the rotation axis. Okay? And so what's going to be the kind of picture if we're rotating this stripe here around our rotation axis? Here in this particular picture I'm drawing, we're rotating around the x-axis. All right, so here's the picture. That stripe, and it's straight. It's a straight stripe. Drawing it, rotating it, we're going to have a nice empty cylinder. Nice empty cylinder. And that's why, ladies and gentlemen, that's the name right there. It's a cylindrical, okay? It's that shape being a cylinder. Okay, but then here's the thing. This cylinder, I'm not talking about a one solid cylinder. It's only a thin cylinder. Has a thin cylinder that's having, it's completely empty space inside here. It only has a very thin surrounding roll right here. Okay, that's why it's a shell right here. Like imagine like a drum shell right there. A drum shell, it's a cylindrical shell right there. Okay, so I can instantly just think about, allow me to do this quick demonstration. This piece of paper of mine. Okay, so now if I roll that together so that it looks like a rotation, okay, then it is now a shell right here, a cylindrical shell. So what we have here in the picture is a cylindrical shell right there. All right, and so just imagine with this shell, this roll of paper where so empty spaces in here. So right in front of the camera, empty spaces here, empty spaces here. Okay, and then this is the shell that's going around. Okay, all right, so it's circular because we're rotating. So the stripe, if we're looking on flat view, the stripe, this is where the stripe came from. This is the stripe, and rotating it, it gave us the whole roll of paper. It created a shell here, and that's the method that we call it's the cylindrical shells. Okay, so now that you having a better idea right here, and that's why cylindrical shells. So now that's why we can have so many shells like that. If we're putting it here, we have another shells, right? And if we put our stripes here, and of course again all of these stripes are parallel to the rotation axis, to that rotation axis. So if we rotating this shells, we have an inner shells. Okay, so this time right here. All right, so those are the shells like that. And so the idea now is that we're gonna, again, I have to constantly remind anyone who is about to use a calculus, who is about to apply a definite integral into solving a volume problem. You gotta constantly remind yourself, an integral itself, a definite integral itself is accumulation. So here, calculating volumes of this solid here using cylindrical shells, what are we doing with that? So each cylindrical shell, okay, has a volume. Now I'm not talking about how much volume that it's covered. I'm not talking about this roll paper. I'm not talking about this roll paper here. I'm not talking about the volume of the space being inside the roll paper. Nope, because this space here, as I got clear with viewers, this is empty space. So we don't need to worry about that volume. We worry about how much the volume of this thin roll, right there. Okay, or it's just the volume, see, or we standing it like this. Okay, then each shell like this has, this is the thickness right here, how thick our paper roll was. Okay, so this is thickness, we got thickness. So in this case, this is thickness. All right. All right, and then there's thickness, there's height or length of the stripe. Okay, or if we're standing at vertical, we call it height. It's same meaning. All right, and then we got thickness, we got the height, and that should be enough to give us, and it's of course it's a circular shape on the two ends right here, but it's empty space in the middle. Okay, and so we're going to be accumulating all of those volumes, shell volumes, okay, volume of the thin shells. We're accumulating all the volumes of those thin shells like that from a starting to an end right there. And I'll get clear about where the start has to be and where the end of the accumulation has to be. But that's the idea of calculating volume of using of a rotation solid right there, of a rotated solid using cylindrical shells. Okay, so let's have a quick look at the other picture. So what's going to happen to our shells? What's the picture of our shells if we're rotating that around the y-axis? Because earlier I was doing the rotation around the x-axis. Okay, so now again, here's our region. Okay, rotation axis is here. We're still rotating it. All right, but this time imagine the number one requirement is that any of our stripe has to be parallel. So the stripe this time has to be parallel with the rotation axis. So that's why I'm drawing it that way. Okay, and then so now, just like how we saw it through the other picture, you gotta turn on your imagination. Okay, so imagine what's going to happen to this stripe if we're rotating that around. See, I take the same marker here, that's this stripe, I rotate that around. What kind of shape are we going to create? We're going to create a cylindrical shell. It's a shell that we're going to be creating. Okay, and so this shell, just like how I argued earlier, just like how I explained earlier, this shell is going to have an extremely thin volume, the thin volume that's wrapping around. Maybe I was not using this term, but now I feel that the term wrapping around is the most precise term at this point right here. The thin, think about the thin shell that's wrapping around. So the thin shell itself has a volume where this is thickness, okay? See, that's the stripe right here, the thickness of the stripe. And then there's a height, because the stripe is currently standing upright right there. So there's a height right there. And that should be enough to calculate the volume of that thin shell. And then we're going to accumulate, because the whole volume here is going to be calculated by accumulating all the shells, okay, from a start to an end right there. And again, I will get clear. I will get to the point where we really going to be clear about where the accumulation starts and where we generally end our accumulation. Okay, and so that's the idea with the cylindrical shell right there. That's the brief idea with the cylindrical shell. And so now I need to point out a few more details right there, so that we can start bringing that philosophy into an actual example. And so now here's the thing. I'm going to erase all of these extra shells, because we only need to pay our attention to one shell, and that should be good enough for our problem to work with. Okay, so our x-axis is here, the rotation takes place around, so I'm going to erase the big shell here and all of the little shells. I'm only going to need that mid-size shell. Okay. All right. So here's our region that's rotated, to be rotated. Okay, that's the region, and our shell is here. Okay, so as I explained earlier, in this picture, see, the shell has its own length once we created it. Okay, once we rotated that, the shell has its own length. Okay, the shell has its own length. But see, this length right here changes. This length right here changes depending on which shell that is, and the length. And another thing you have to understand, the length of the shell is completely contained. This time, the stripe that we're putting here makes no sense to go outside, to cross through the region and go outside of the region. So it makes no sense that way. Okay, like the disc and the washer methods, and there are cases where the stripe goes through, gets outside of the regions to reach to the rotation axis. But in our case here, using cylindrical shells, we're producing cylindrical shells, and there will never be any case where the stripe goes outside of the region at all. So in other words, any stripe will be completely contained inside of the region. Okay, and so now in that, along with what I'm pointing out right there, then the length of our stripe right there must be determined by the length varies. Okay, the length of the stripe varies depending on where we put that stripe. And so here you can see that it varies mainly from, on one end of the curve to the other end of the curve right there. So on one end of the boundary to the other end of the region boundary. Okay, so we're gonna get to that as well. Okay, so that's the length. So you can realize that the length varies right there. And then as I said earlier, any shell that we're looking at, that we're looking at right here has so in this case right here, see, this small amount, infinitesimally small, is regarded as the thickness. Okay, and then we have the length, so I'm going to label that here. This is called the length, And then let me erase all these extra notations here, notes right here. All right, so we have the length of any stripe is there. So when we're creating that, so again, allow me to use that paper roll demonstration. Okay, I'm gonna wrap this paper around. Okay, this paper itself has already had thickness. Okay, and now I'm gonna wrap it around like this. I'm gonna wrap it around like that, and in front of the camera, I hope that can be clear enough. I'm gonna wrap it around. Okay, and so here's my cylindrical shell. That cylinder. Okay, that has a thickness. The thickness is here. How thick that is? The part that's wrapping around. The thickness is here. The part that's wrapping around. So if I'm putting that this way, there's a thickness. Okay, but so here's how we calculating. Because remember, I said earlier, what the whole point now is that we're gonna be accumulating the volume of all of these cylindrical shells. Okay, all cylindrical shell volumes. So we're not only having one shell, we have infinitely many shells. Okay, so we're going to be accumulating all of those shell volumes. So we have to figure out a way to calculate the volume on one shell. So what's the volume on one shell? So think like this. At one shell right here, the face here is circular. So there has to be and there has to be a radius. A radius is always from the center of rotation. So the center or the rotation axis reach out to the shell. This is where I call that the radius. Okay. So the distance from the rotation axis out to any shell in particular, this is not the stripe. It's only the distance from the rotation axis out to where the stripe is at. Okay, because remember the stripe is here in this case, and we're working with stripes, that is any stripe that is parallel with the rotation axis. And so this is the radius. And the radius determines how big or how narrow our cylindrical shell is. Okay, when it becomes, and this is really a pipe shape. If the shell is long enough, it's a pipe shape right there. Okay, but now anyway, so it's circular, so it has a radius from the rotation center out to the stripe. Out to the stripe itself. That's become the radius once we're rotating it. Okay, and so now here's how I'm formulating the volume of one thin shell right here. Think about the piece of paper. Think about, and then let me put a vertical version, a standing up, an upright version of the shell right here, like a drum shell. Okay, so we have thickness. Okay, that's part right here. No matter how thin or how thick that is, and we're in calculus now. We're talking about infinitesimally thin. So this is the thickness, but being extremely thin and keep getting thinner. We have thickness and we have the length. Okay, so this part right here is the length. Okay, and then the rotation axis is going through like that. Then here's let me make a note of that. That part right there is the radius. All right, and so now to calculate the volume of that, imagine that from where your shell currently is, as a wrapped around, as a rolled around piece of paper. Okay, in looking at that in front of the camera or looking straight at it like this, standing straight up like that. Okay, the thickness is here. The thickness is how thick this paper is. Okay, and so imagine to calculate that. Surprisingly, the volume of this thin shell is nothing but just the volume of this piece of paper when we unwrap that, when we unroll that, when it's unrolled, when it's flattened out. This piece of paper when it's flattened out. All right, so let's find out. When it's flattened out, then any shell when we flatten it out, it becomes one rectangular piece of flat sheet right there, like a sheet of paper, just like what is in front of me right now. And once we unroll it, and so what will the thickness become? The thickness the thickness of the paper. Okay, but that length, the height right here will become the width. Okay, and the long side of this piece of paper is indeed the circumference of the shell, the circumference of the shell when we rolling that. Okay, so again, let me repeat my philosophy. Let me repeat my argument here. It might go slow for anyone. I already said this earlier here. I'm just repeating it. So if you feel like you already got the idea, then you can skip this part right here. But the volume of the one thin shell will be exactly equal to the volume of this piece of paper when we unroll that piece of paper, when we unroll that shell. Okay, when we unroll that shell, then the volume of the shell is exactly the volume of this thin sheet of paper. So there's thickness. The thickness of our shell become the thickness of this sheet of paper. See how thick that is? We can't even see that even in front of the camera. I can't even tell. Okay, so the thickness is here, the thickness, and now this is the circumference, the circumference of the shell. Now I'm talking about circumference because the shell has a top and bottom being in circular shape, and so the circumference of the shell after being unrolled becomes the length of the sheet of paper. All right, and so now that height here, the height, in case when I'm standing this vertically up, I'm standing my shell vertically up, then the height, or the length of the length of the cylinder becomes just the width of the sheet of paper. So we got length that comes out from the circumference, equivalent to the circumference, and then the width right here of the sheet of paper, and then there's thickness right here. All right, so in that way, so now I can start having a formulation. So really, imagine that, let me draw a different version. And on the space of my board right here, I see this is the shell that we're doing, but let me try to put in your imagination a shell that still has some noticeable, some recognizable thickness. Okay. All right, so this is thickness right here. That's thickness. And then we have thickness, and we have, see, this is length of the shell, and we have circumference. So now to find the volume there, all we do is, and imagine that flat version, then all we do to calculate the volume of that shell, I will go back and set up the formula as following. We will calculate the volume of the shell, okay? The volume of a shell, of one shell, is going to be equal to, now the circumference, because the circumference is just when we unwrap this paper, okay? But the circumference, when we wrap that around, then the length of the paper here becomes the circumference, okay? And so any circumference is known. The circumference in that, the circumference is that's going around the circular end right here, that circular face right there. Okay, so circumference is known to be 2 pi r. 2 pi r. 2 pi is a constant, and r is how much the radius from the rotation axis out to the shell itself right there. Okay, so this is this is radius. That's distance right there. This is radius. All right, and so now in that case, circumference 2 pi times radius. Okay, circumference times radius. That's, imagine it's, that circumference is equivalent to the length of the piece of paper when we're unwrapping it. Okay, and then circumference multiply. We need to multiply with, and I don't want my writing to interfere with the picture, so I'm going to write it a little lower down here. Okay, it's a 2 pi r. We multiply circumference with the, so circumference is equivalent to the length of the paper, but now it's the width of the paper right here, which is now in this case the length. The length, okay, we're multiplying that with the length and multiplying that with the thickness, okay. So my picture is getting a little too much now, so let me erase part of that. Length, and we're multiplying that with the thickness. That's always one rule for how we can calculate the volume of one shell. 2 pi r is the circumference. Multiply with the length. Okay, This is the length, and we multiply with the thickness. That's the volume of one shell. Okay, that's the volume of one shell. And so just like that, in my board over here, see, circumference depends on the radius, 2 pi r, multiply with the length. Okay, that gives you basically just the circumference multiply. Think about with high school geometry, only this part right here where we have circumference multiplying with length here, that gives us this. In high school geometry, we call that it's the surface area, or the lateral area, the amount of area that's wrapping around, only wrapping around on the side like that. Okay, lateral area by multiplying circumference with the length. And then we multiply that with the thickness. The reason we multiply with thickness because this unwrapped version has a thickness. So even with the wrapped, the roll version, it also has a thickness. So we multiply with thickness. That's the volume for one shell. Okay, the volume of one shell. And so now, in that way, my picture is starting to get a little, my board is getting a little tight right here. So allow me to erase a lot of this. Okay, so here's the x-axis, and now that's the volume of one shell. We are now going to be doing a accumulation. We're accumulating all of those. We're going to be accumulating all of those stripe volume. So this is a shell volume. Okay, this is a shell volume, but we're going to be accumulating all of those shell volumes from a start to an end. All right, from a start to an end, and that's how we are going to get the total volume. Okay, that's how we are going to get the total volume. All right, so this is the main fundamental I want anyone learning with me to get right there. The part inside of the, and this is now an integral. Accumulation is an integral. Okay, so the part that's inside the integral here, that's the formula setup for the volume of one cylindrical shell. Circumference is 2 pi r, circumference. Okay, or if the shell is going this way, okay, circumference. Multiply with the length, that's how much lateral area that is. And then we're going to multiply with the thickness. So there's always a little bit of thickness there. Okay, and then we're accumulating all of those stripes from a start to an end. And that's how we obtain the total volume. And this is what we call that. It's the methods we're accumulating cylindrical shells. Okay, and so now in this way of explaining right here, I have to get clear a little bit. So start and end. Now it will come to at some point outside of this lesson, if I have some time, I will make a short clarification. But otherwise, if I put all of that details here in this video, it's going to be too lengthy. But for now, keep it one rule of thumb right here. When we're accumulating, okay, we're going to be accumulating from those stripes. We're going to accumulate this. Basically, the start of our accumulation start with those stripes that closest from the rotation axis to the further out. So we're accumulating from the inside out. Okay, and inside out, I mean from those stripes, from the stripe that's closest to the rotation axis. Remember, any stripe is parallel with the rotation axis. So we accumulating from the stripe that's closest. So we have a closest stripe here, okay, and we're accumulating out. Okay, so that's what I mean by inside out, and that's the way right there. Okay, and so make a note on that for me. Start is it's called the inside, and then end of the accumulation is the outside. Okay, and inside and outside, I'm short of space, so allow me to explain verbally over here. Inside means the inside is the stripe that's closest, okay, closest to the rotation axis. And then inside, outside, so we'd end at the outside one. Outside here is the furthest one for here, the stripe, whichever stripe that's furthest away from the rotation axis. Okay, so that's what inside out means. All right, and so now we are enough for getting into our first example. All right, so here we are at example 1. And so after this particular lesson right here where I call this the general discussion lecture on the cylindrical shells method right here to find volume of those solids generated by rotating a region. I will be providing additional examples right there, but they are outside of this lesson right here, outside of this lesson. But in those examples there, I will produce as many as I can. But the more you view, the better you learn experience. But within this lecture, I will be delivering about 2 examples where they are connected. Okay, they are connected, and then outside of this, I will have, like I said, additional examples. But I will only relate to the general understanding from this video lecture only, and those examples that I deliver later on outside of this video lecture is completely on your own will to watch. The more you watch, the more experience that you're gonna gain in using the cylindrical shells method to calculate the volume of these solids right here. Okay, and so now allow me to bring up example 1 right here. So we want to, and I have to spend some time state the wording right here. So we want to evaluate, okay, or how about compute or calculate, okay, compute the volume of the solids, okay, generated by rotating about, okay, so here I'm just gonna first indicate the rotation axis, so rotating about the y-axis. The region enclosed by. All right, so the segments connecting the 2 points 2, 1 and 4, 5. Okay, so we have 2 points on the coordinates plane right there, and the segments. So this is the description of the enclosed region. There's a segment connecting those 2 points right there. Okay, and there's the line x equals 2 and x equals 4, and the line y equals 0. This is really nothing but just the x-axis. Okay, and that's the x-axis. So basically, here's our region. It's the region enclosed by that segments connecting between the 2 points is 2, 1 and 4, 5. Okay, and then with these 2 lines right here, x equals 2 and x equals 4, and then with the x-axis. So the 4, really this middle one right here, because I'm trying to save space, so I write these 2 in one line, but this is 2 graphs right here. Okay, this is another one that makes 3, and this is of course the 4 graphs all together that enclose our region right here. And we're going to take that region and rotating that about the y-axis. Okay, we're rotating that about the y-axis. Okay, so now as I finished now writing down the description, the wording description of the problem like that. Okay, you might want to pause the video and write down the problem as well. Okay, and so now let's have a look. I'm going to turn over to Desmos on my computer screen to see the graph, the quick sketch. And at this point, this needless to say, the problem did not ask for that, but it is highly recommended that you do a sketch. So even though a lot of problems in these days will not ask you to make a sketch, but it's extremely beneficial that you make a sketch right there. And the sketch will help you imagine your rotated the solid. What will it look like? Okay, and so in this way right here, let me turn over to my computer screen right there. All right, so here is my blank graphing space right there. Okay, and so the 2 points 2, 1 and 4, 5, the line that's connecting, this is the line right here. This is the line that connecting the 2 point 2, 1 and 2, 1 and 4, 5 like that. It's a straight line. So it's really part of a straight line. So now let me put in the other 2 lines right there. See, this is x equals, I purposely hid away all of the numerical wording right here, but right here, okay, right there at this intersection between the line in red and that other section between the line in red and the line in black right here. So there's 1 intersection, there's 2 intersections. This point right here, see, 2, 1, okay, and this other point is 4, 5. All right, and then the x-axis is here. So the region enclosed is the region inside of this. All right, so now let me put in the actual region like that. All right, so the enclosed region has to be this region. It's being trapped inside of the 4. It makes no sense to be that region out here. It makes no sense to be any of the regions here or even there. Nope, it's not any of those. So it has to be this region here. All right, so now in restricted view right here, the region we're looking at is only this region right here. See, these are the 2 points, 4, 5 and 2, 1, and the segment connecting that. Okay, and this is part of that line. X equals 2 and x equals 4 is here, and the x-axis gives me part of that, the boundary of the region right here. So we take this region and we're going to be rotating it around the y-axis. So here's our y-axis. We're going to take that region and rotating it around the y-axis. All right, and so now let's have a look at what the solid is going to look like with using Desmo to generate that rotated solid right there. So here's our region as we've seen in the 2D version right there. And now I'm going to rotate that. So here's our line that connecting the 2 points. The 2, 1 is here in that at that vertex, and 4, 5 is here. And this is the line. This is x equals 2. This is x equals 4. Okay, and then the x-axis is here, or the line y equals 0 is here, and so this shaded, this region shaded in blue right here will be rotated around the y-axis. Now the orientation of the axis does not matter, so here let's look at the rotation. All right, so now if I'm rotating halfway, okay, and allow me to stop it about halfway, that's the kind of region we're going to be expecting. And this is not new. If we're learning this lesson after we have already seen the disc or the washer method. So rotating a region around an axis, any axis, this idea is not new. But now how do we see the shells here? So now let me put in the shells. All right, so now see, if I at any x value, if I place a shell, see the shell now be the stripe being the stripe. So let me roll back to the beginning point right here. See? All right, so in the beginning the stripe is here. All right. And then as we're rotating it, now once we start rotating it, then the stripe become a shell. Okay, and that's why it's just now observing it. See, now we're creating a shell. The shell is the red one that's being created as we're rotating. All right, and so now when we complete the rotation, then that's how we have the shell, the red shell right there. And so now the idea of the accumulation. For the idea of the accumulation, we are accumulating from the inside out. So, all right, so from the inside out, so inside is about here, okay, and then inside out. And so if we're accumulating all of those stripes like that, right, from the inside out, and that's how we're going to get the total volume like that. So each shell in red picture, each shell in the red picture right here will be having a volume on its own. Okay, and that's how we get that picture. That's how we calculated the volume of that picture right there. All right, so on this board of mine right here, the picture looks as following. All right, so 2, 1, and of course I'm going to be a little bit off scale right here, and then 4, 5. Okay, so we have a picture like that, and then here's our picture as you have already seen with Desmo like that. All right, so here's the region to be shaded. And then so now that region I'm rotating around the y-axis. Okay, so the idea, the fundamental, so at this point the fundamental of the shell method, here's how I'm putting the shells. So once we identified the problem gave us the problem according to the description of the problem right here, then we know that we have to be doing we rotating this region around the y-axis. We cannot change that. It's what the problem tells us to do. Okay, but at least what we know here is that we will place stripe. We will put any stripe to be parallel. So our stripe is here this time. This is my stripe. Okay, and the stripes only stays completely contained within the region. And you can see now the length. Let me put another stripe. The length of the stripe changes depending on where we put the stripe. Okay, and so now in this setting, for this particular problem in the setting, here's our x-axis, here's our y-axis. Imagine if we take this stripe right here and rotating that around the axis. Here's our picture. And maybe if I drew this stripe a little too far away, okay, allow me to draw the stripe right here. Okay, so there's how we built our cylindrical shell. So there's we have our shells right there. Okay, and now we're gonna have so many shells right there from inside out, because rotation axis is here. So the closest later on when we get into the accumulation, we're gonna be accumulating from inside out. This one here I call it in because it's the stripe that's closest to the rotation axis, and that stripe, whichever the stripe that hits the furthest point of our region, that stripe is the outermost one. Okay, and we'll get to that later. But now in the way how we're standing the stripe right now, it's just right in how we see the picture, just right in how I see the picture. Okay, then the thickness. All right, the thickness is here, right in the picture. Okay, and then circumference, or from where the rotation axis out to where the stripe is placed. The rotation axis out to where the stripe is placed. That's this part here is the radius. Okay, and then so we have thickness, we have radius. When we have so let me draw another arrow over here. So the arrow pointing here is this is going to be the height, or some other time I call it length. Okay, the length of the cylindrical shell like that. So that's all the information we need about the shell that we have. So now in that way, again, that fundamental I was introducing, all we need is to calculate the volume of one shell first. Come up with a generalization to calculate the volume of one shell. So, and recall for yourself, any shell we're going to calculate by 2 pi r the circumference of the base circle. We're going to multiply that with the length. Okay, and in this case, eventually I'm going to refer to that as the height, because our cylinder here is standing upright. The circumference multiplied with the length, that gives us the lateral area of what's wrapping around the shell right here. And then we're going to multiply that with the thickness. Okay, we're going to multiply that with the thickness. And then that's the volume of one shell. Then we're going to be accumulating from the inside out. Okay, so now let me get even clear. Start to end is the same as the inside out. And inside, I mean this, from wherever the stripe that was placed closest to the rotation center out to the furthest one. And that's what inside out means. Inside out. So the thickness, and then this is inner, this is outer. Okay, so we're accumulating from inside out. And that's how we're going to get the volume. Okay, and so this is the way that, and I will hopefully at some point, at the end of this video lecture, or at some separate one as a short clip, I will explain why it has to be inside out. Because I've had students when classes, when I'm teaching a face-to-face classes, I have students raising a concern. Why is it not? Shouldn't it be the same as outside in? Because it's just accumulation. Okay, I agree, but it will give an opposite answer, but I will have to get to that clear explanation in a separate video clips. Otherwise, doing that here, giving all of that details here will make the video very lengthy. So for here, all I'm asking is anyone learning from this video lecture, keep the accumulation to start from the inside and end it out, inside out. That's where our accumulation goes. And inside, again, I mean from the closest point, from the stripe that's closest, from the closest stripe, with the rotation axis out to the furthest stripe right there. Okay, and that's how it goes. And of course, it makes sense to be right in this region right there. All right, so now we're going to start deriving. Okay, and so you can see right in the picture over here, the way how I place my stripe, we have to start putting on, we have to start turning on our imagination. We need imaginations, okay? So go ahead and, you know, triggering up your imagination right here. The thickness, in the way how we place our shell like this, the thickness has to be, okay? So let's make a list right here. The thickness, okay? And it's just me that personally I like to start out with thickness. Okay, so thickness here, in the way how we place our stripe, it has to be a dx, because it's going to be a change, it's going to be a difference, even though at the end, eventually it has to be to that level when it's infinitesimally small change in x value. So that's why the thickness here deserves its own, deserve to be regarded as a dx, because it's on the x-axis. It's an infinitesimally small change in x. All right, and we're going to put that as part of our accumulation formula right here. So now I have from the inside out is accumulation from the inside out, and I'm going to partly filling in, the information. Okay, so I still need to find out what the length is, what the r is, but now thickness can be expressed as dx. And so this is the reason why I personally like to start out with the thickness right here, because thickness gives me a d expression. And with that d expression, now it gives me a clear indication that any of these have to be expressed as a function. If we recognize, once we recognize that these are variable quantity, then we have to express these in terms of x, because the d expression here in our integral is already prepared here, is already indicated here, and that kind of drives the way for us right there. So now we know that all of our quantity here, if they are variable quantity, then they have to be the expressions in terms of the x variable. Okay, so now from that way, then we have a lot more control between the radius and the length of whichever one comes before the other one. That's completely on our choice, on your choice right there, doing this. So I would go with radius. Okay. Radius is, again, the rule here is the distance from the center of rotation out to the stripe. The distance from the rotation out to the stripe. And then the radius does change too. At some stripe we have more distance, some stripe we have closer. But see there, from where the foot of our stripe is standing, right? In the way how we place our stripe, the foot of the stripe stands right on the x-axis. The foot of the stripe stands right on the x-axis. And in that way, that's why now the radius here, we have a perfect expression for that. It's just x. Because our rotation axis is right at x equals 0. So out to anywhere here, it's going to be x. That's the rotation. That's the radius. The distance from the stripe, the foot of the stripe, down to the rotation axis. All right, so that's x right there. That's how I recognize my radius. Okay, and now, once again, another checkpoint for consistency right here. But is this radius, see, it's a variable expression. And now have we expressed that variable expression as an expression in terms of x? Yes, we have. Okay, that's how I always check myself when I'm doing these work right here. Okay, and then, so now we have just that length of the stripe right here as a remaining part. So the length of the stripe, any length here, the length of the stripe varies as well, right? Depending on where we place the stripe. So if we place the stripe here, it's shorter than where we place the stripe here, and this stripe is shorter than the other stripe at the very last stripe. And the very beginning stripe right here is the shortest one. So what do we think right here? See, it looks like in this picture, it looks like the stripe is, if we treat this curve here, this is the segment. See, the problem, I only, in my intention, I only want viewers, or I only want students of mine to see this segment here only as a line, as a graph, as a segment that's connecting these 2 points. But now in the context that we're in, then we must, see, a line is just a line, a graph is just a graph, but now we must write this graph here as a function of x. We must write this line right here as a function f of x somehow, so that at any x value, at anywhere x value on the x-axis, at anywhere on the x-axis where we place our stripe, then we would have a way to calculate the height here of the stripe, as the output value of our function in terms of x right there. And that's the point. So once again, I repeat, the problem only, and right in the first example, I put the problem a little complicated in the sense that it's not directly given as a function, but I want my viewers to have that generality that all you need to understand is to stay in this fundamental. And then how we derive these depends on how the problem is being, how we sketch the problem. So the length is the length, and we realize that the length varies depending on where we put the x. Okay, and then the length is determined by the distance between the x-axis out to that curve, out to that line being the segments connecting 2, 1, 4, 5 like that. And so that length here, that segment here now must be expressed. That segment must be expressed as a function f of x. Okay, as a function f of x, so that at any x value, we will know that the height here, okay, or which is also the height of the stripe, will be the function output value of that function f of x. Okay, but that should be simple enough. Quick little scratch work right here. All right, the segment here connects 2, 2, 4. 2, 1. Okay, and 4, 5. It has to be a line. It's a segment, so it's a part of a line. So we need so f of x here has to be in the form of an mx plus b. It's a line. It's a famous equation for a line right here. So slope here can be found by, that means m has to be, see, rise 5 minus 1 over run 4 minus 2 right there. So 5 minus 4 over, 5 minus 1 over 4 minus 2. And so that gives me 4 over 2, which is 2. And so that means now I'm going to see that my slope here is f of x is 2x plus b. And so now once I found what my b value is, once I found what my slope value is, I can just simply take either one of these pairs of values. This is just completely algebra, so allow me to go brief on this right here. I'm going to pick one of the 2 pairs of values right here and substitute that into the function. So this is the function output, or this is the y value. Y value, substitute for that. X value is here. Okay, and I choose this pair simply because the values are smaller. And so here I'm going with 1 equal 2 times 2 plus b. And that consequently leads to b has to be in value negative 3 right there. Okay, and so now that means we have f of x here concluded to be 2x minus 3. 2x minus 3. Okay. F of x equals 2x minus 3. This segment right here, it means, that function here means this segment right here is part of the graph, it's part of the line 2x minus 3 right there. Okay, why is this information beneficial for us? Well, now I need to erase that to make space for my later steps. Okay, but what I see now is that the length, okay, the length or the height, okay, the height or the length of our stripe is determined. See this, at any radius x right here, or at any x value where we place our stripe, because it's on the x-axis, then the length of the stripe is f of x, or in this case right here, 2x minus 3. Or I can just, for short, say f of x equals 2x minus 3. Okay, and so now in that way, I'm ready to put both of these informations into my integral formulation right there. And so now it's going to be 2 pi, the radius here is x. Okay, the length of any of my stripe is 2x minus 3. Okay, and so now that completes my setup for the volume of, this is volume of one shell. Okay, volume of one shell. And that's why now we're going to need to be accumulating all of those shell volumes from start inside to the end outside, from the inside out. And again, in my explanation, in my logical reasoning right here, inside out means we go from the stripe that's closest to the rotation center out to the furthest one. That's how it goes like that. Okay, so in that way, in the way how the picture looks, see this inner boundary, this line right here is x equals 1. Okay, and now I realize my picture is a little too much. So x equals 1 is here. And this last line right here is x equals, according to the picture, okay, x equals 4. Okay, so inside, out, inside is here, outside is there. And so now I have a complete integral formulation. We're accumulating from, actually, I just now realized I made a mistake here. This is actually 2. So inside is 2, outside is 4. So from 2 to 4. We're accumulating from 2 to 4. All right, so ladies and gentlemen, this complete integral right here is the integral that will get us the final volume of this solid once we're rotating that around the axis. I mean around the y-axis. Okay, and so this is now going to be, realizing that we can have this 2 pi here as a constant coefficient. I can pull it out front, and then from 2 to 4, and then x is distributed through each term here. So I'm looking at 2x squared minus 3x, okay, with a dx. All right, and that, at this point, needless to say, this video lesson should be learned after we have already learned about the fundamental theorem of calculus. So I am going to use the fundamental theorem of calculus to find the final answer for this problem. And so now I've had all of this information here up here long enough. So allow me to erase this because I need more space to show a couple more steps of my calculation, and then I'm going to step over to my computer station to grab the final answer. So according to the fundamental theorem of calculus, we're going to take the antiderivative of this, so which is now a 2/3 x cubed minus 3/2 x squared, okay, and then we multiply with the 2 pi in front, and then we need to be evaluating that antiderivative from 2 to 4. Okay. All right, so allow me to skip that step where I plug in the values. The next step here is the next step from this is simply just to substitute in 4 into the antiderivative and subtract the antiderivative here, substituting in 2, substituted in 2 right here. But since I'm running out of space, so I'll just quickly grab the final answer from my computer station right there. All right, so the final answer according to my calculation on the computer, I came out with 116 pi over 3. Okay, and that is how, this is the volume of our solid that's generated by rotating this area around the y-axis right here. Okay, and so in case anyone, so here's the final answer, but in case anyone really wants to see how I got that, I mean, I really just use a computer to do the calculation, just basic calculation. Again, the fundamental theorem of calculus says we are going to evaluate 4 into the antiderivative and evaluate 2 into the antiderivative and subtracting out the 2. So I have 2 pi times that 2/3, 4 times 4 cubed minus 3/2, okay, times 2 squared. And then I'm going to subtract out, and there's again 2 pi, okay, and there's a 2/3 times 2 cubed minus 3/2 times 2 squared, okay, and that's how, subtracting out the 2 answers here, that's how I ended up with that 116 pi over 3, okay, and that is the volume of the solid that's generated by rotating this area around the y-axis, okay. And so at this point, we can draw out, right at the end of this example, we can draw out a fundamental right here. So I'm just trying to align, but this is just optional details that I'm pointing out right here. Normally, I don't recommend going with formulas because this is the only fundamental, right? But in case any of my students try to synchronize my lecture here or trying to align my lecture here with any standard textbook, with material delivered in any standard textbook, then this is how you will see a lot in many standard calculus textbooks right here. So now I have to erase this. because I need more space, and I want to leave the writing on my other board the same for a later reason, for a later purpose. Okay, so this problem we're rotating around the y-axis, and that's why I'm trying to stay away from being delivering too many formulas, because that will make you remember more cases. So in this particular problem, we're rotating the area. We're rotating the area around the y-axis, and so that's why many textbooks deliver this. We go from A to B, see, inside out. Okay, and then we have a 2 pi. So the radius is always x, as we have already derived. But see, now it's impossible for any textbook to explain all of that details, but it really came from this fundamental. Okay, but like I said, if the textbooks deliver all of that, then it's going to take the textbook being this thick for all of that the logical reasonings. And so that's why a lot of textbooks, you just see straight into a formula, say, hey, if you are rotating a region using the cylindrical shells, using a cylindrical shell method, and when you're rotating around the y-axis, right, then you're going to go 2 pi x times the function. See, the length here, we express our curve as a function times some function f of x dx. This is the version, this is the formula version that you see in a lot of, in many standard calculus textbooks. Okay, but so this is how it aligns with what I explained here. So the 2 pi x here, really that's the circumference. Okay, the circumference of the base cylinder, of the circular base of the cylinder. And so that's why in the situation where we place our stripe, so I explained by the way how you see your stripe. If we place our stripe, of course, parallel to the rotation axis right here. So once we know our rotation axis, and we know that we place our stripe parallel, and it makes sense that radius has to be x. That's the consequence of that. But many textbooks could not. It's just the way it is. Otherwise, if they give to any textbook gives all of these informations in the details, it have to be a very lengthy textbook like that. So that's the radius, and then generally speaking, the idea now is that we express the length or the height of the shell by the distance from the x-axis out to wherever that upper curve is, and that upper curve is generally expressed as a function f of x. But see, now you have one formula. You already have one formula for the case where we're rotating around the y-axis. Okay, we're rotating about the y-axis, and it's starting to become hard to remember because I've seen many students in my past teaching experience, they have to fight pretty hard and try to distinguish between, if it's the y-axis, if you're rotating around the y-axis, then you write in terms of x, and then the other way around, like that. But that's in the end too many formulas. Plus, when you're all in one calculus 2 course and you've learned about this method, the washer method, and the cylindrical shell method right here, then it's going to become way too many formulas to remember. So I write this down, the formula, the version that's aligned with the textbook. But in the end, I recommend any of my students who study directly with me to keep this fundamental over here. This is the only one fundamental, because it doesn't matter which axis of rotation that you're doing, you will always stay with that fundamental. Okay. All right, and so now we are going to head into example 2 of our the same lecture here. We are trying to calculate the volume of a solid that is generated by rotating a region around a given axis. And so I still have example 1 in the back on my backboard right here. Okay, on the board behind my back right here. But the reason I still keep example 1 here for so long, the writing of the example 1 for so long here, is simply because I want to show that when I'm creating example 2, I can just simply alter a few the pieces of information from example 1. I only alter a few pieces of information, and we're gonna have example 2. So let's see which pieces of information will be altered here. Okay, so yes, here we will call that example 2. It's pretty much the same wording, and so leaving it there, it saves me also sometimes writing down the problem like that. So I want to compute the volume of the solid generated by rotating about this time. I'm no longer rotating around the y-axis, but I'm going to rotate around the x-axis. And so that piece of information now is being altered. Rotation axis changed to a different axis. Okay? And then the region here that we are rotating. So we're rotating around the x-axis, the region that's enclosed by the segments connecting those 2 points. So it's still that same segment, connecting the 2 points. Yeah. Okay, but this time I'm going to change these. Okay, I'm going to change these to, all right, how about y equals 1 and y equals 5. All right, and then another graph here, I'm going to alter this. I'm going to change this to, how about x equals 0. This is indeed the y-axis. All right, so the pieces of information, those are pieces of information that are altered is this one here, that one here, this one here. Okay, and of course we change it to the x-axis. Okay, and so now we're going to take that region and rotate that around the x-axis. So whatever region, we will have a look at that on the graph right there, but whatever region that is, we're going to take that, imagine the x-axis is going this way. Okay, and so we're going to be rotating that around the x-axis. Okay, all right, and so now let's have a look at the graph right here. So here's my blank graph, okay, my blank graphing space right here. Okay, so now let's have a look at the region. So the line that's connecting, the segment that's connecting the 2 points 2, 4, I mean 2, 1 and 4, 5 is this line right here. Okay, and then start and end. So y equals 1. Okay, so I have that line. I have that point, I have this point right here. Okay, so this segment, this line right here is connecting between the 2 points 2, 1 and 4, 5. Just like how we had that in example 1. Okay, let me put the points back on again. All right. And so now those are the points that our line is connecting through. So and then we have a line y equals 1. Okay, and y equals 4 is, and I mean y equals 5 is here. So y equals 1 and y equals 5. All right, and then the x-axis, I mean the y-axis, the line x equals 0 is here. So the region enclosed by the 4 graphs there must be this region. Okay, and so now I'm going to just turn the graph into just the restricted version so that we can, hide away these unnecessary the lines right here. All right, there we go. So now that's the region that we are going to take this region and rotate that around the x-axis. Okay, so the x-axis is here, and rotation the center of rotation should not matter. I mean the orientation of the rotation should not matter right here. Okay. All right. So unlike example 1 right here, let's have a look to see how the rotation happens when we're rotating that region around the x-axis. Okay. So our region in blue here is that region, and then the line, this horizontal line right here is the line in this horizontal line is our x-axis. Okay. And this line right here is our y-axis. Okay, and so there's the region. Now I have to do a lot of work around to have this rotation because I never had time to prepare one on my own. But nowhere over the web I can find a resource showing the rotation around the x-axis that has that deals with the shell method. So I have to do a little bit of work around. So I apologize for the mouse cursor here looked a little weird and odd on the screen right there. Okay, but now this is the rotation, okay, and along with that we can see that there's a stripe that's coming along. Okay, so the stripe is here, so there's a stripe. So okay, so that part right here is a stripe. All right, and so now as we're rotating, then the stripe is going to become our shell like that, and that's why along the x-axis, okay, along the x-axis we are going to see a shell, but this time the shell is being placed sideways, and it's empty space in the middle here. In this part here is the empty space. Okay, All right, and so maybe it's better to roll back to the point where we only just rotate it about halfway so that we can see better the shell, okay, any shell, and then the rotated region. And then again, just for about the shell itself right here, we're going to be later on accumulating from the inside out. So, okay, so inside out. All right, inside out. Okay. All right, so now let's return to the board and make a hand sketch version, and so that we can see more clearly about how we placed our stripes, so that we can create and we can have a better picture of the shell right there once it's created, any of our shell right there. Okay, so now I'm gonna navigate over to my other board right there. All right, so here's my graphing system, x and y axis. Okay, y-axis, x-axis is here. And then I have a point at 2, 4, okay? 2, 1 and 4, 5, that same point right here, 4, 5. All right. But this time the region we're looking at, and you have already seen that with decimals right here. So here's the line connecting the two. Okay, but the region that I'm rotating is this region. All right. And yes, I'm making shading to make it clear about the region. But now we're gonna, in the way how we're doing, we want to rotate this region around the x-axis. And like I have already explained, the orientation of the rotation should not matter. Okay, so we can go counterclockwise or clockwise. We're still going to end up with the version of the solid right there. We're still going to end up with the same solid. And so after that, then the whole idea again, in what I explained earlier, we're going to place a stripe, but this time the stripe has to be parallel with the rotation axis. So the x-axis is the rotation axis in this problem as required by the problem. So here's how I place my stripe. So my stripe has to be parallel. Okay, my stripe has to be parallel with the rotation axis. Okay, and then so now imagine now, so now we're going to start putting that in our imagination that what's going to happen to this stripe once we're rotating it. And we're going to create that, and just like you saw with the rotated on decimals, with the rotated animation with decimals, we're going to have our cylindrical shell that looks like this. Our cylinder shell that looks like that. Okay, and then so now we're going to be, see, and then inside out right here. So there's a shell that's closest. There's a shell that's closest to the rotation axis, which is here. Okay, and the shell that's further out, the most further shell is up here. Okay, but so anyway, let's get the problem handled over here. So fundamentally, again, just like things that we have drawn out from example 1 right here, the only fundamental that I want anyone learning with me to catch is that we have to figure out a way to calculate the volume of one shell. And think of that thin roll of paper that I wrapped and that I unwrapped. So I did so many times of that illustration so that you can get the idea right there. Okay, but so the one shell here, for one shell, it's going to be 2 pi radius. Circumference of the circular face right here, of the circular ends, bottom end and upper end right here. And well, we're putting our stripes, we're putting our cylinder here sideways, parallel, wrapping around the rotation axis in this case, so it's kind of sideways. But see, this side right here is what I call the length. Okay, this is the length of the shell. This is this small distance right here is seen as thickness. Okay, and then the radius is whatever the distance from the rotation center, okay, out to where the shell is, from the rotation axis out to where the shell is. That's the radius. So I make notes, okay, of a couple of those quantities. And so again, back into any shell, the volume here is the circumference of each shell right here, because it's round, nice and round, circular, top and bottom. And then we're going to multiply with the length, okay? And we multiply with thickness. That's how we get the volume of one shell. And then we're going to be accumulating to obtain the total volume of the solid here by accumulating all of those shell volumes from the inside out. Okay, so this is you know, as soon as you arrive at example 2, you will see this, the fundamental twice right there. Okay, and then of course from that fundamental things will start going into different paths right there, but it's all coming out from this fundamental, and once you catch and stay aligned with that fundamental, you will get any of your cylindrical shell method problem done successfully. Okay, and that's how, and this is how we get the total volume. All right, so keep that fundamental with you. So let's find out again how we can track down these quantity like radius, length, and thickness of our shells right there. Okay, so it's just my personal favorite. Okay, I will always start out with nailing down the thickness. So again, look at the picture. In the way how I see I place my stripe, and the way how I place my stripe comes out consequently as the way how the problem describes for us, how the problem requires us to do. We want to rotate this around the x-axis, so I have to place our stripe under that requirement. The stripe has to be parallel with the rotation axis. That's the requirements right there. Okay, so in that way, how we place our stripe, you know, align with the requirements and follow with the problems like that, then the thickness here has to be the dy. It's a change in y value. See, the stripe is being placed the parallel with the x-axis. That means it stands, the foot of each stripe lands right on the y value. So the thickness here is the infinitesimally small change in y value, or in other words, it's dy. And so now once we've had thickness, we can start filling in our accumulation formula right here. Okay, an integral is accumulation from the inside out. To calculate this volume, we're accumulating shell volumes from the inside out. 2 pi r circumference. I have not found the radius, the generalization of the radius yet. I have not found any generalization for the length yet. Let's leave it there, but the thickness now I know is a dy. Okay, so thickness is dy. So at least in my way of approaching it, and in my style of teaching my students, I want my students to always focus on this d expression on any integral. So the d expression here now is indicating dy. That means that we know it is our responsibility to express length of the shell and radius of the shell in terms of, as expression in terms of y this time. Okay. And so now things can start. It's the same line connecting the 2 points we have seen in example 1. But now we have to find our way to express. You see, so first of all, about the radius for the stripe. The radius, rule of thumb, is always, well, as a requirement, the radius is the stripe is parallel with the rotation axis. So in that way, in the way how we place our stripe right here, then the radius, as a rule of thumb, is the distance that comes out from the rotation axis out to where we place the stripe. Okay, the radius is the distance from the rotation axis to where we place our stripe. And so in this case, in this case right here, in the way how we're placing our stripe, this radius has to be expressed in terms of y. It's just how much y value. So it could be a different y here, and when it gets to here, it's a different y value. Perfect. We have an expression for the radius in terms of y consistent with that y. Okay, and that's why I yelled out loud, perfect. Okay, this is number 2 right here. That's radius. Okay, so now that's just simply y. Okay, so now I'm going to fill into my expression here. It's a 2 pi radius, but now radius is y. 2 pi y. All right, and now I'm going to find out how I can express length here as a function of y. So think about it, and it's also consistent with the fact that the expression here has to be a y expression. It's a dy right here. So that's why I was saying that. That's why I knew I'm looking for a way to express the length here in terms of y as a function of y. All right. So now the length here, you can see any length of the stripe varies depending on where we place our stripe. So at any y value, if we're at this y value or at y value here on anywhere on this y-axis, right? If we place a stripe parallel to the x-axis, then it looks like the stripe is the function output if we can express that line here in terms of y. Okay, and so So now, similar experience how we've had done that in example 1 right there. So now in example 2, I have to re-express this line right here. I have to re-express this segment as a function of y. But see, anytime as long as I put 2 examples in one lecture, that means they are somehow still connected. We have already found the equation for that segment as a function in terms of x from example 1. So technically we can start all over from scratch here, constructing the equation of this in terms of y. But once we have already done something in example 1, we can reuse the information here and make a little tweak. Okay, so here's how my argument is. So from part A, from example A right here, we already expressed y equals 2x minus 3. That same line connecting the 2 points, the 2, 1 and 4, 5. That same segment right here is part of the line y equals 2x minus 3. That same line. Okay, so now, but that was in part A, we expressed the graph as a function of x. We don't want this. We want the function in terms of y in this case here, because obviously our height, our length of the stripe is how far from the y-axis out to the curve itself. So it's better that we express this line here as an expression as a function of y. So it should be a simple work here. I'm going to add 3 from both sides. Okay, I'm going to add 3 from both sides, and that gives me 2x. Okay, and I'm going to divide both sides by 2. Okay, that gives me, and that will definitely give me, in the rule of algebra, it gives me now 1/2 x plus 3/2. All right, equals x. So now I have expressed, and that should have been y. All right, so 1/2 y plus 3/2 equals x. This is how I have expressed my same curve right here. It saves me some effort. If this problem is completely started out as a brand new problem, then you have enough algebra. I believe anyone viewing this video will have enough algebra. This is only one option that saved me some effort, save viewers some effort, in case the problem here you done here is related to some other problem that you have already had some results. Okay, and so now in the end, the bottom line is we have to find a way to express our length here of any stripe as a function of y. Here we have had it here. Okay, and so now that means I'm going to take that result and fill it in my board right here. So the third step, as we track down, as we're identifying the length of our stripe, then it's going to be, we're expressing that as x equals a function of y 1/2 y plus 3/2. That's our function. Okay, that's 3/2. All right, so that's our function, but now completely expressed in terms of y. And so now I'm ready to take this function, express it as a function of y, and substitute that into my length. Okay. And so now I can clear this away. And so with my integral right now, it's going to become, so the length here, we have 1/2 times y plus 3/2. All right, and so that's how it works. So now at least this part right here is the volume, okay, of one shell. This is the volume of one shell. Okay, and so now I am going to be accumulating all shell volumes from the inside out. So let's identify in this picture where's the inside and where's the outside. Once again, that rule of thumb, that fundamental, I ask anyone who's viewing this video lesson to stay with me, is that and I will hopefully have it shouldn't be too important. You can also derive that on your own as well. But we go from the inside out, okay? And inside means the closest one. So if you're looking for y always inside out right here to give you the correct answer, then that's the part where I said hopefully I'll have some time to put it in a separate video lesson, because it shouldn't be too important to have that in understanding. But so here we keep it as a rule that we're accumulating the shells from the inside out. But inside out, I mean inside out from the stripe that's closest to the rotation axis. So this stripe right here is closest. Okay, that's inside out. So in that way, the inside here, it looks like we're at, this is y equals 1, and this line right here is y equals 5. Okay, y equals 5. So now inside out means I'm accumulating all of my stripe volume, all of my shell volumes from 1 to 5. Ladies and gentlemen, now we have arrived at our complete setup of the integral that calculates the volume of this solid once we once we rotated that region around the x-axis. Okay, so just like that. All right, so now just like that, once we're rotating, okay, the picture here is hopefully looking close enough to the picture I have on the board right there. See, there's the x-axis, there's the y-axis, and now I'm going to be rotating it. All right, so as we're rotating, we're going to get a picture like that. Okay. All right, and so now back to the problem right here. Now I can see that I can pull out the 2 pi right here as a constant coefficient. So I'm leaving that as a 2 pi here. And then in the meanwhile, I'm going to multiply that y to each term in my problem. And the problem turns out to be a surprisingly simple integral. And we have everything consistent with each other. The thickness here is dy, so it gives us the d expression in terms of y in our integral. And so everything else is now expressed in terms of y. So we're pretty much ready to go. And so I'm integrating from 1 to 5. I'm going to distribute that y to each term here. So I'm looking at 1/2 y squared plus 3/2 y. Okay, and I'm going to be integrating that in respect to y. Okay, so now allow me to erase this work right here. And so now what I'm looking at here is a 2 pi. Okay, and according to the fundamental theorem of calculus, I am going with so 1/6 pi cube plus, and then now I'm going to have 3/4 y squared, and then I'm evaluating that from 1 to 5. Okay, from 1 to 5. And so I will show the actual calculation steps later in case anyone need to know, in case anyone really want to know. But then here, let me quickly step over to my computer station and grab the final answer here, and I will express my final answer in exact expression. Okay. All right, so my answer came out to be 232 pi over 3. All right, so that's the answer that my computer at my desk station gave me right there. Okay, so the actual calculation based on the fundamental theorem of calculus is simply, now I'm going to have to take away some space right here, but we're going to go 2 pi, right? That antiderivative 2 pi times 1/6, but now we're going to substitute 5 in there at the cube. Okay. So I'm trying to explain where that value comes from, even though I use the calculator that's a lot faster. Okay, so it's 3/4 times 5 squared. So that's the antiderivative evaluated at the upper limits, and then I'm going to subtract, and then there's a 2 pi. Okay, and here I'm looking at 1/6 again times 1 cube plus 3/4, okay, times 1 square. All right, so doing this setup right here will arrive us at 232 pi over 3. All right, and that's how we have done another problem with finding the volume of a solid generated by rotating an area, okay, and using the cylindrical shells. All right, so again, before I'm completely closing down this example right here, and this is also at the end of this example, it's about where we're ending with our general discussion lecture here on the shells method, on the cylindrical shells method. Then again, if in case any of you love reading your textbook, you will see your textbook will indicate the following formula. Okay, so now let me clear away the result of our problem. Okay, and as far as the calculation step right there. But many problems, the case we're looking at here, unlike example 1, is that we are rotating the region around the x-axis. So many problems, many standard calculus textbooks will deliver the following formula. Okay, circumference is 2 pi y. Okay, and then times with the function, some function g of y, multiply with some function g of y, and then multiply with thickness dy, and then we're integrating from the inside out from some value c to d. Okay, so there we go. We have another formula, and this formula, to make it consistent with what I was explaining here, the 2 pi y here came from circumference is here. That's circumference, 2 pi r. Okay, but it will, you know, if for any textbook, for any author of the textbook, it's going to take a lot of writing and printing, a lot of pages to explain all of that detail. So, you know, usually you see a formula without too much explanation, without much possible explanation right here. And this is for the case of about when you're rotating about the x-axis. Okay, about the x-axis. All right, so if that's the version of the formula you are seeing with many standard calculus textbooks. But again, at the NC, after 2 examples, if you tend to remember formulas, then you're going to have a lot of formulas to remember. So both problems that I was doing were circulating around that only fundamental. 2 pi r, the circumference, times the length of your shells, either standing it vertically up or horizontally sideways here. That's the length of the shell, multiply with the thickness. And from there, we're going to look at our picture and start tracing down all of those other ones. I used my own experience to teach with the where I placed down the 3 different steps right there to get the thickness first. That's just my personal favorite right there, to get the thickness first, and then the radius, and then the length right there. Okay, and then once you have the thickness, we would be having a clear identification for ourselves about, you know, where, you know, should that be a dx or dy. And once we've had that, then should we express the function or the rest of the other variables in terms of x or in terms of y? We will have a clear indication for that. Okay,